Okay, our problem is this cylinder. It's metal. Everything, the walls at the bottom are at potential equal to 0, but the top is held at potential equal to negative V sub 1. What we want to do is find the potential inside the cylinder using Laplace's equation. To do that, we're going to use separation of variables. So right away, if I take the Laplacian of this, I'm going to have to use a formula for the Laplacian in cylindrical coordinates, and I'm going to notice there's a term with the derivative of v with respect to phi. That's going to go to 0 because our physical situation doesn't depend on phi whatsoever. So I'm going to end up with two terms, one depending on s, the radial distance, and one depending on c, the height. So do a little bit of algebra and end up with these two terms here. Here I have to use the reasoning that for these to constantly sum to 0, they both have to be constant because they depend on two different variables that are independent of each other. So right away, I know I have these two constants and they're equal and opposite, and I'm going to choose C1 equal to minus k squared and C2 equal to k squared, and I will talk about why I made that choice. Okay, so I rewrote these diffie-q's. Our z equation looks like a harmonic oscillator. Did a little algebra on the s equation, and we get this interesting second order differential equation. To solve it, we had to do some research and find the Bessel functions, which are the solutions to this. It's a second order equation, so there's two linearly independent solutions, which would be the Bessel function of the first kind and the Bessel function of the second kind. In the case where we chose the opposite sign for k, and we had minus here, we would get the modified Bessel functions. So to determine that this should be a plus, we had to look at just the graph of these functions and match those to the physical situation. So the modified Bessel functions, these don't work. The first kind never crosses 0, and radially on our cylinder we need it to get to 0 at the outer edge. And this modified Bessel function of the second kind diverges at the origin. The Bessel functions Bessel function of the second kind, it also has a singularity at the origin, and that is not physical because our potential should be finite inside this cylinder. The Bessel function of the first kind could be a solution to our physical situation because it is at a finite number at the origin, and it's going to go down and cross 0, which would be at the wall of the cylinder.
All right, so from what Boaz had when he solved the Bessel equation, we know that our solution to S must be the Bessel function of the first kind, order 0, multiplied by Ks, and then multiplied by a constant. We can't have any other ones Bessel functions of different kinds because they all blow up. And of course, if we chose negative k for the S function, then for the z function, we must be using positive k, and in that case, we're going to have an oscillator that immediately decays, and there is no repeating oscillation. Okay, so now we simply have this and we plug it into our original ansatz. Our original ansatz was that voltage is a multiplication of S and Z, so we simply just substitute in the expressions we have right here, and we get the following. And now it's time to apply the physical intuition, the boundary conditions, and start trying to solve for C, A, B, K, these unknowns we have. So again, take a look at the cylinder. We have voltage must be negative V1 at the very top where Z equals H. Voltage must be 0 at the very bottom. And then voltages at the sides where we're at the radius S equals A must also be 0. Okay, so let's just pick one of the boundary conditions and apply them, right? We know that voltage at the very bottom of the cylinder is 0. So we set these equal to each other. We plug in 0 for Z. E to the power of 0 is always 1, so we have this expression right here. And take a note here. So J naught of Ks, this is like an oscillating function, right? So there's going to be some points where it's not always 0, and that means that we can't rely on this to zero out the expression at Z equals 0, because this is going to vary. So this cannot always be 0. Now what if we set C equals to 0? If we set C equals to 0, then we will never be able to satisfy the boundary condition on top, where the voltage at the top is negative V1. So because we can't satisfy this equation using either C or K, well then we know A plus B must be 0. So in this case, you can just pick one that is going to be the negation of the other, so I pick B equals negative A. Alright, so now when we plug this back in, B equals negative A, we just plug that back into the expression we have here, and we factor out the A. And this expression right here, e to the kz minus e to the negative kz, well, this is just 2 times sinh. The plot itself, let me find a marker. The plot itself of sinh is going to look something like this right here. So, so again, these two are equivalent. You can always double check that on Desmos. And then we can absorb the 2 to the c as we usually do in calculus and get this expression right here. All right, so now let's keep moving on. So we still have 2 unknowns, right? We don't know what k is. We also don't know what c is. So let's start applying more boundary conditions. So we know that voltage at S equals A must be 0. The outer shell is 0 voltage. Okay, so we just plug that in. And okay, what can make this expression 0? Well, we know that C cannot be 0, again, because of the earlier reasoning. And also sinh of kz, well, this is only 0 at the point at the very bottom of the cylinder. This is not going to be 0 anywhere else. So we can't rely on sinh to 0 at all. We also can't rely on C. So that means J naught of Ka must be equal to 0. But the thing is right here, J naught of Ka equal to 0, we know that the J naught oscillates up and down like this. So there's going to be multiple points. There's going to be multiple points, multiple values for Ka for which this function is 0. Now, which one do we pick? We can pick here, 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 and we don't really know. So what we're going to do instead is we're just going to pick any root. So Ka must be equal to any root, and we denote this root as little jn. And the final voltage, we say, we're going to guess that it's going to be some sort of combination of many different k values for the Bessel function of the first order, and it's going to be summed like this. All right. Okay, so now that we do that, we have this expression from applying boundary condition 2. Now let's apply boundary condition 3. Boundary condition 3 is, we know that the voltage at the very top, where Z equals H, must be negative V1. Okay, so we just apply that over here, and we set them equal to this expression that we built up a little bit earlier. Now, how do we solve? Now, we can see like the one thing that we're missing is this Cn right here, right? So we need to solve for Cn right here. So how do we do this? Well, there's this property that we need to use called the orthogonality property. So, according to Wikipedia, if you have a Bessel function with the 0th root, and it's part of this expression right here, where the parameter for the phase is equal to the nth root, and both are n's, then the resulting equation is the Kronecker delta multiplied by this expression right here. And because we have a Kronecker delta here, it means like the only way which you get a non-zero result from integrating two Bessel functions together is if their parameter values are equivalent. So we can exploit that orthogonality property to try to solve for our Cn. So what we're going to do is we're going to multiply both sides by j naught of k gamma s and then times s. Now this is slightly different from the orthogonality property for cosine and sine because we have to have this extra s parameter. But that's just part of the property of the orthogonality for Bessel functions. So we multiply both sides, and we're trying to get to this part right here where we can cancel out all these summation n's and we only have one n. So we multiply both sides by j naught k gamma ss, and then we start integrating. We go from 0 to a, so let's go from the center of our cylinder to the outside where radius r equals, or s equals a. Okay, so we have this expression here, and now we know that because of this Kronecker delta right here for the orthogonality property, we can just get rid of all these n's. There's only one specific n that's going to make it so this expression on the right is not 0. Okay, so we set them equal to each other, and we simplify, get rid of the summation, and we end up with this expression right here. Okay, so now we have two different integrals to solve, right? We have one where we're integrating this, we have two where we're integrating this. So let me pull up to the back side of the board over here. Okay, so now we're doing negative v1 times the integral of 0 to a of, j gamma k gamma s ds. All right, so how do we approach this? Well, we know that there's this property where the integral of x times j naught x s is equal to j1 of x plus c. And we need to get this, this parameter here in the form of this. So we just do a u sub here, where u equals k gamma s, and du equals
Good evening. The library will close in 30 minutes.
k gamma ds, and 1 over k gamma du is equal to ds. And now this parameter here, this a would become k gamma times a. This parameter bottom stays 0. S is equal to u over k gamma. Okay, so let's simplify this. So we have v1, and it equals to the integral of negative 0 to k gamma a of u over k gamma, j gamma, u, and then 1 over k gamma du. And the gammas don't depend on u at all, so we can pull them out, and we're going to end up with negative v1 over k gamma squared times the integral of 0 to k gamma a of u j gamma u du. Oh, and sorry, I typoed here, but there's actually still an x here for that property. Okay, so now we just apply this property to that property, and we end up with negative v1 k gamma squared times u j gamma plus 1 u, and that goes from 0 to k gamma a. And then now we plug in k gamma a into this u. For the second part, the 0 times this expression is obviously 0. So you have negative v1 k gamma squared times k gamma a, j gamma plus 1 u, and then these gammas cancel out and we end up with negative v1a over k gamma, j gamma plus 1 u. Okay, so that's one of our equations that we just integrated. So now we need to integrate the second one. Okay, so let me just pull that from the back. So we have the integral of Cn sinh knh, j naught kns, and then s ds. Okay, so we have the integral from 0 to a of Cn sinh of kns, and then let's see if I remember, jn, the kns, jn to the kns, and then d, we multiply both sides by s, so we have s ds. Okay, so how do we do this equation here? So we know that our property, our identity, states that we integrate from 0 to 1. So recall 0 to 1 of jn of kns j little jn little jn s times s ds is equal to, now I'm gonna have to look back on the back because I don't quite remember this one. Right, the Kronecker delta 1/2 times jn squared. So again, if they're equal, Kronecker delta over 2 of jn plus 1. And let's see, do we have a equation there? It would just be jn squared. Okay, so we need to get this equation in the form of this. So how do we do that? Well, let's do a u sub. So remember, we said that kna must equal to jn. In other words, we must land on a root of the Bessel function. Okay, so we need to put this in the form of this. So let's replace kn equals to jn over a, right? So let's add that over here. 0a cn sinh of jna s jn jnas jn jnas sds. Oops, yes. So now let's do a u substitution. Let's do u equals s over a. So du must be equal to ds over a, and a must be equal, or adu must be equal to ds, and we also need this, we also have an s here, so we also have to set s equals to u over a by our u sub, and so now we can just plug everything in. This sinh is not going to depend on, oh, just kidding, it will. So it'll be 0, this is s over a, so this becomes 1 of cn sine h of cn we can pull outside. So it was cn over here. And I'm remembering that we're finding the boundary at the very top where the sinh is, where we have, I think this should be a z, let me double check. K and h, right. So again, the sinh only depends on z, and we're at the very top where the voltage is equal to negative V1, so we can also pull that out. So Cn sine h, Kn h, and we have the rest of our u sub here, which is just Jn u, Jn, Jn u, Jn, and then this s right here is UA, this ds becomes a du. We can pull this a squared out And then we'll end up with Cn sinh knh times a squared, integral of 0 to 1 of jn u jn u jn u du. And we can just apply our identity here, where the result of this should be equivalent to this right here. So this is equal to Cn of sine h knh a squared multiplied by 1/2 jn plus 1, so this becomes also jn plus 1, and then multiplied by jn, just simply jn squared. All right, now we have these two halves of the equation right here, and we need to combine them back with what we had previously. So let me grab another whiteboard. Oops. And let me erase the Bessel functions we had earlier. Okay, so our original expression had these two set equal to each other. So I'm just going to copy them down. Negative V1A K gamma J of gamma plus 1 U is equal to C. I mean, we can kind of interchange gamma and n. They're going to be the same thing because there's only one value for both, which the two will equal. But I'll just use gamma. A squared times 1/2 jn plus 1 jn and squared. And so we just need to solve for the C gamma here. So if we just divide both sides by this expression here to the right, we end up with this over sinh k gamma h a squared 1/2 jn plus 1 jn squared. We can move the 2 up here. The a maybe cancels there. I might have typoed a little bit earlier. But negative 2v1 j gamma plus 1 u over k gamma, and then sinh of k gamma h jn plus 1 jn squared, and this cancels with this. We have the a here still. So this becomes 1, and this cancels. And we get negative 2v1 a k gamma sinh k gamma h jn plus 1 jn. And now since we have this expression for C, we can just plug that back into our original equation. So recall that we set v equals to some constant, or the infinite summation from -1 to 0 to infinity of Cn multiplied by, let's see, I believe it was J naught K gamma S, and then times our sinh function of K gamma Z. So if we just plug in this equation into here, we get the summation of n equals 1 of negative 2v1 we can pull out. We can also pull out the a, where we get J naught K gamma S sine H K gamma Z, and we divide that by K gamma sine H K gamma H Jn plus 1 Jn.
Okay, this is a contour plot of a slice inside the cylinder showing the potential. The vertical axis is the z-axis and the horizontal axis is the s-axis. So we see that it's smoothly going down from 0 at the bottom and the sides to negative at the top. This is a 3D plot of the electric field, which we can calculate in Python by taking the negative gradient of our potential. So we would expect at each surface, the top forms an equipotential surface and the bottom and sides form an equipotential surface. So at each surface we would expect the electric field to be perpendicular to the surface, and that matches what we're seeing here. It's pointing in at the sides and the bottom, and then at the top it would be pointing straight up.
The charge density of the cylinder based off of Gauss's law and our equation for electric field that we have here. And we weren't quite able to ascertain what the electric field was outside the cylinder at the very top, so we left that as a question. But we found an expression for the charge density of the side of the cylinder. It's this expression right here. Basically, this sigma naught times, or epsilon naught times the R component of the electric field. And we found that it went from basically a charge of 0 to a very high positive charge density as we approach the edge of the cylinder where Z equals H.